video, we found the area under the graph of x squared from 0 to 3, and we did that by breaking up the interval from 0 to 3 into a bunch of smaller ones, and then drawing a bunch of rectangles, and for the height of the rectangles we used the value of the function somewhere in the interval, and then we added up all the answers of the little areas, and then we took a limit as n goes to infinity. Well, it turns out this whole process has a name. So the idea of finding these areas by adding a bunch of small areas where you have the width is delta x and the height is based on the function f of some value x here. These are going to be called the Riemann sum. And then we take the limit of these and we're able to find the true area. And we're now going to use this notation here to indicate what we're talking about. So for this answer, this area up here that we got, the area was 9, we would now write that as the definite integral from 0 to 3 of x squared dx, which just means the area underneath x squared from 0 to 3. There is a little bit of a problem here though when you're doing these Riemann sums, is if you think about it, if we're using the how high the function is, the y value, in order to have the height of our rectangles, then if you have a graph like sine, and you get to this second half and you're drawing rectangles down here, then you're going to have a negative y value. And if you have a negative y value in your Riemann sum, you're going to get a negative area for that rectangle. And so it's entirely possible to have some positive area, some negative area, and some cancellation as a result of that. And so that's why we don't actually say that the integral is just the area. We say the integral is going to be the net area. The positive minus negative all canceled out, the best you have, that's the net area. So for the sine example, if I found the net area from 0 to 2 pi of the sine function, it's actually going to be 0 because the positive area and the negative area are going to perfectly cancel each other out there. It works out really nicely. Now, there are a few properties of these, some of which we aren't going to use all that often, but still good to go over. The first is that if you switch your order of what left and right are, then you are always going to get the opposite of what you got originally. So if I wrote down the integral from 3 to 0 of x squared dx, I would in fact get negative 9 for the answer. Now you might say, well, that's dumb because why would I say 3 is the left and 0 is the right? The problem is when you're doing some sort of a general problem and you don't really know what your starting and stopping values are, so you put them in as variables, and then later you found out that you actually switched something around at some point in time, the thing you called the start was really the stop or vice versa, then you would have essentially the wrong one, but it just turns out that we don't have to worry about that. We can just randomly pick either one to be the start and the other one to be the stop, and by this property here, it'll all work out to give you the right answer anyways. If you get a negative, then you realize, oh hey, maybe I messed up something in the beginning of the problem. The second one, also pretty straightforward, but not super useful. Just says if you integrate or you find the area where you start at one point and you stop at the same point, well, that means there's no width to your rectangles, so the area is going to be 0. That's all there is to that one. Now with that said, this one here, the next one, this one's pretty useful. It just says that if you are adding or subtracting functions inside, you can just break it up into two separate problems, find the area of the first shape and the area of the second shape, and add or subtract them. We will definitely use that one over and over again. The next one after that is when you have constants, you can always factor constants out, and they're going to multiply the whole area. So again, just lets you simplify things. Instead of having to deal with 5x squared, you could just deal with x squared and multiply the answer times 5. This last one here is kind of interesting. it says that if you're trying to find the area from A to B, you can pick some point in the middle, which I called Z, and you can first find the area from A to Z, and then find the area from Z to B, and you just add them up, and that will give you the total area. It's just saying that you can break up a shape into two smaller shapes and add up the areas. That's really all it's trying to tell us here, but it's written in some way more complicated notation. And then we come to the single most important thing here, one of the most, if not the most important thing in the whole class. This is in fact the reason why we say that Newton invented calculus, because he came up with this, or Leibniz, depending on who you're talking to. There's two different inventors of calculus. But regardless, this is it. And in fact, a lot of the stuff that we've seen, there was similar ideas to that before Newton and Leibniz, but it was realizing this connection here that is what catapulted it to its own field called calculus now. And it's telling you that if you want to find the definite integral, which is the net area, if you want to find that out, you can skip the whole drawing out of rectangles and taking limits. You can skip all of that work. Simply find an antiderivative and plug in the endpoints. So if I'm trying to find the area from 0 to 3 under x squared, I can just say, well, an antiderivative for that is 1/3 x cubed. And then this is the notation we read, or we write. This means plug in x equal to 3 and x equal to 0 and subtract. That's what that notation means. So if you plug in 3 here, you get 1/3 3 cubed minus 1/3 0 cubed, and you get 9. And instead of taking 20 minutes to do a problem, you can do it in 30 seconds. So this right here shows you the power of being able to find the antiderivative function. It's going to let you find areas involving that function very, very easily. And if you can't find the antiderivative, you simply cannot use this method, and you have to go the really long way. So this is why we're going to want to get really good at finding antiderivatives. With that said, there is another fundamental theorem of calculus. It only works when you have a function defined as an integral of another function. It is not that commonly used, to be honest. In fact, you'll probably use the regular one that I told you 100 times more than this one, but it does come up occasionally. And it tells you that if you define a new function as the integral of the old one, and you take the derivative of the integral, you get back to the function you started with. As I said, it's not something you use that often, where you take the derivative of an integral like this, but regardless. Anyways, so I will tell you, if you're ever reading in books and things, the Fundamental Theorem of Calculus, this bottom one, which I called other, they call that one the first, and they call this one the second. And it doesn't really matter which one you call which, but definitely I would say the one they call second is the more important one here.